The greatest of human endeavors is a risky business.
Yes, we've had a problem here.
NASA led the world into the exploration of space, but behind the scenes, out of the public eye, mistakes, mishaps, and failures plague the space industry.
Obviously a major malfunction.
Discover how NASA space failures further exploration. NASA's often forgotten predecessor, NACA, the National Advisory Committee on Aeronautics, was created in 1915 to compete with German aircraft design in World War I. NACA moved American aeronautics from those early wooden wire, cloth and a prayer biplanes of yesteryear to the world's very first supersonic flight of the rocket engine-powered X-1, piloted by future astronaut Charles Chuck Yeager in 1947. 11 years later, on October 1st, 1958, to compete with Russia's successful launch of Sputnik, NASA was born. Between then and now, NASA has brought us the Mercury program, Gemini, and the first American spacewalk, Apollo and the Moon. 30 years of the Space Shuttle program and the International Space Station. Tomorrow, Mars and beyond. NASA's success with each groundbreaking achievement, from the distant past to the far future, depends on the knowledge gained and the technology developed for past programs. And while technology is fundamental to space travel, the most vital factor in NASA's successful journey into the great beyond is its people, their creativity, courage, and motivation, and their bold and endless drive to go where no one has gone before. Being human also means making mistakes. Decades of research has shown that most space failures are caused by human error.
Look for an impact.
An astonishing mistake sends a $100 million deep space probe spiraling out of control, dooming priceless cargo in a spectacular crash landing. But first, NASA is forced to scrap a critical and expensive piece of space shuttle hardware when a technician makes a wrong turn. NASA's highly sophisticated Coordinate Measuring Machine Probe, or CMM probe, measures machined parts on any axis, down to less than a micron. NASA's CMM probe is used, among other things, to measure components of the Space Shuttle orbiter's cold plates.
A cold plate is used to draw the heat from the LRU avionics and radios in the shuttle.
Inside the Space Shuttle orbiter, line replaceable units, or LRUs, including avionics boxes, control numerous critical functions of the orbiter. The LRUs produce a lot of heat, which cannot be traditionally vented or cooled because of the sealed environment inside the crew module. Cold plates are installed against the LRUs, and the heat is drawn off through convection, keeping the LRUs cool. Failure to cool the LRUs properly could be fatal to the crew. The cold plate's core material is machined into a single component that includes more than 30,000 individual protruding pins. The pins are designed to meticulously control the flow of coolant through the cold plates.
They have to be very precise because when we're done building the cold plates, they flow a fluid through them during testing, and it has to flow at a certain rate to make sure that it's going to flow fluid through enough to draw the heat out.
Machining those 30,000 pins is a precise, time-intensive, and expensive process, a process that can take weeks to complete a single cold plate.
You have about, I'd say at least 80 manufacturing hours, probably 2 shifts, 2 weeks to machine that, because each one of the little pins in there is machined individually.
Then each and every one of those 30,000 pins must be checked to ensure that it meets precise dimensional requirements. This meticulous process is accomplished with the CMM probe.
They take detailed measures to make sure that everything matches the print requirements.
Operating the probe is fairly straightforward, but in a bizarre accident, many hours into the process of checking every pin, unexpectedly, everything goes wrong.
I was measuring the part. I need to move to the next area to measure. I need the machine to move upwards and over.
But instead of moving up, the probe suddenly goes down, damaging the cold plate and the CMM probe.
Instead of moving upwards, it went down. And during that time, it ended up damaging the part, causing a hole, a dent, and also the equipment at the same time.
Technicians are stunned and confused. A cold plate has never been damaged in the CMM probe shop. Why today? Was it a technology failure or operator error? NASA's investigation would reveal why a 15-year veteran operator's perfect record suddenly came to an end. a highly sophisticated coordinate measuring machine probe in the hands of a meticulous, experienced operator, and the unthinkable happens. A space shuttle cold plate is damaged, along with the mission-critical CMM probe. CMM probe operator Fred Vivier calls his supervisor immediately to tell him what happened, but he doesn't believe it at first.
It took Fred a while to convince me that that's what had actually happened. Some of my inspectors are practical jokers occasionally, so when he told me he'd done it, I just, nah, you didn't really do that. It took him about 20 minutes on the phone to convince me that they had actually done it, because you're talking a lot of man hours, a lot of machine hours into making that part.
Sick. A really bad sick feeling came over due to the type of part, time taken to make the part, and the criticalness of the part.
Fortunately, damage to the CMM probe is limited to the ruby tip on its stylus, which is quickly replaced. The cold plate's a different story.
The probe ended up springing into a very, very thin wall on the cold plate, causing a dent and a small hole.
The cold plate core is scrapped. It no longer meets NASA's strenuous safety requirements.
Pretty detrimental to the program at the time when we're trying to, meet a schedule.
So this set us back. We just had to go build another core.
Building another core would take at least 80 man-hours, a costly operation. Manufacturing a new cold plate and repairing the ruby-tipped stylus solves the hardware issue, but doesn't answer NASA's most pressing questions. How did it happen, and why? Questions that had to be answered before any other cold plates could be inspected. NASA could not risk damaging another mission-critical piece of hardware. NASA needed answers, and fast. The CMM probe involved in the accident was new. It replaced an older machine that had broken down. The machine's software and mechanical functions were working perfectly. But like so many other space mistakes through the years, the accident was a result of one simple human frailty: operator error. A 15-year skilled operator with a flawless record made a wrong turn, costing the space program tens of thousands of dollars and weeks in delays.
I mistakenly twisted it the wrong way and it went down instead of up.
But this was not a simple case of lack of attention to detail. The operator was one of the best in the business. Why did he make such a costly error?
There was no rush.
Knowing Fred as I do, he was concentrating on what he was doing.
I think it was the way the machine was set up.
Had that thing been oriented right, it would have never happened.
The old machine had different controls. The probe was controlled by 2 joysticks. The new CMM probe was controlled by a single, multifunctional joystick.
The one joystick will make it go up, down, right, left, forward, and backwards. If you twisted it clockwise, it would go up. If you twisted it counter, it would go up. It would go down.
But the cold plate was destroyed when the controller was turned the wrong way. While this might not be a big deal in your latest home improvement project, this was NASA, and this was unacceptable. The measurement of cold plates had to be foolproof. Investigators were closing in on both the root cause of the accident and a solution that would guarantee future success. When the new CMM probe was purchased, each technician spent hours training on the new machine.
Once we got it in here and all the folks went through some specialized training, that was part of the purchase contract with it. I had like 4 inspectors at that time. They all went through a week's worth of training with the company rep where we purchased the machine.
But the root cause came down to the human trait known as automaticity, a pattern or habit resulting from learning, repetition, and practice. Walking, driving a car, or always putting on your right shoe first are examples of automaticity. These ingrained habits are formed from years of repetition, even by some studies altering our brain patterns, making relearning or unlearning certain habits extremely difficult. The new controller required that the joystick be turned clockwise to go up, but the technicians were trained by years of experience that clockwise was always down.
I guess it's our American standards, righty-tighty, lefty-loosey. You want it to go down, you turn it right. You want it to go up, you turn left.
1 week of intensive training on the new machine was not enough to counter years and years of subconscious habit. And putting more space shuttle hardware at risk while the technicians developed new habits was unacceptable. Through extensive coordination with the manufacturer of the new CMM probe and software engineers, the programming was altered to make the probe go up when turned counterclockwise and down when turned clockwise. This ensures the probe is far more intuitive for the operators. One additional fail-safe was put in place. Directional labels were added to the controller.
Have not had one problem since then. We label it, the folks look at it, they take the time they need. We haven't had any other issues at all.
Look for an impact.
Next, a spectacular crash incites a spectacular recovery effort to salvage a $100 million mission and billions of years of science. August 8, 2001, NASA launches a Delta II rocket out of Kennedy Space Center that carries an unmanned vehicle into a little heralded search for the origins of the universe. It's a quiet launch, except for the roar of the Delta II's engines. There are no lawn chairs on the beach, no space fans on top of campers, no massive crowds cheering as the Delta soars away from its launch pad. You'd think there would be, because this unique scientific mission is in many ways traveling back in time, billions of years to the very birth of our solar system. After years of preparation, the world's scientific community is filled with anticipation for what the spacecraft might bring back. The unmanned spaceship is called Genesis because it heads into space seeking answers about the beginning. Genesis is on its way to an orbit within an orbit, 1 million miles from Earth, in direct line with the Sun, to catch some rays and return them to Earth. The spacecraft is armed with a variety of unique collector arrays designed by NASA to capture the purest solar wind ions possible from the outer layer of the Sun. Scientific evidence suggests this outer layer hasn't changed since our solar system was born from its original nebula some 4.5 billion years ago. Ions in the solar wind have been called the fossils of that nebula, which means theoretically they should tell us if our solar system is made up of the same stuff that made up that original collection of ice, dust, and gas. If so, NASA believes those solar winds could also hold clues to the origins of life itself. The Genesis mission is the first time space matter has been returned to Earth in 3 decades, since astronauts brought back samples from the Moon. On November 16, 2001, Genesis slips into an elliptical orbit around Lagrange point L1. Lagrange points are gravity-balanced zones between celestial bodies, and L1 sits directly between the Sun and the Earth. As Genesis orbits L1, L1 orbits the Sun. L1 was selected as the focal point for this critical mission in part because at 1 million miles away, it is void of Earth's atmosphere and contamination. After establishing its orbit within an orbit, Genesis deploys its solar panels to draw energy from the Sun. Then, the primary collectors open and are exposed to the solar wind. The ions from the solar winds begin crashing into the collector arrays, traveling over 200 kilometers per hour, almost 25,000 miles per hour. On impact, the ions are buried into the surface of the collectors. The hexagon-shaped wafers consist of a variety of super-pure materials, including silicon, commercial sapphire, gold, and diamond-like carbon film, some expected to capture the elusive solar wind better than others. Secondary arrays are automatically deployed when Genesis encounters special solar wind, like coronal mass ejections. The purity of the ions is critical. NASA wants pristine fossils of the birth of the solar system if they are to have maximum scientific value. Throughout the years of planning and manufacturing, the collector arrays were handled with extreme care in clean room environments, with a focus on maintaining the critical purity required.
These samples will be available for the scientific community for decades to come.
For 850 Earth days, the solar wind blasts Genesis. Then, on April 1, 2004, after completing 5 halo loops of the Sun, the collector arrays are retracted and stored in the Sample Return Capsule, or SRC. Then Genesis begins its million-mile journey back to the future. Genesis has spent 2.5 years collecting the solar wind ions. The final phase of the mission will be the SRC's entry, descent, and landing. NASA is not taking any chances. An elaborate EDL is planned to ensure the capsule returns as gently and safely as possible to protect its ancient cargo. Traveling over 24,000 miles per hour, Genesis would smash into Earth's atmosphere and immediately begin slowing from the atmospheric resistance. This rapid deceleration triggers a series of mechanical events that deploy a drogue parachute, which stabilizes the SRC and slows the spacecraft's descent. The SRC continues to slow until it is 6.7 kilometers high. The drogue chute is released, and a large parafoil is deployed to further slow the descent and leave the return capsule in stable flight. Then, to further safeguard the precious cargo, a helicopter with a 5-meter-long hook would capture Genesis by its parachute and gently lower the spacecraft to the ground. NASA selects the United States Army's Dugway Proving Grounds as the landing site. Located about 85 miles southwest of Salt Lake City, Utah, it is a vast desert wasteland. Founded in 1942 and notorious for top-secret chemical and biological warfare testing, including the rumored release of the nerve agent VX in 1968, killing over 6,000 sheep 30 miles away from its test site, and the production and mishandling of live anthrax as recently as May 2015, Dugway is highly guarded and its airspace is restricted. It provides a vast, isolated area for the landing of the Genesis capsule. Weeks in advance of Genesis' return, NASA rehearses the mid-air capture multiple times.
6 November, you got a tally on a parafoil?
Scientists around the world have been waiting for 3 long years for Genesis' return. NASA is ready, confident in their recovery plan. Genesis sample return capsule enters the atmosphere right on time on September 8, 2004. But then, everything goes wrong. The capsule begins spinning wildly out of control, plummeting to the Earth at hundreds of miles per hour, leaving NASA scrambling to save the mission. Stunned, NASA watches helplessly as the capsule filled with the mysteries of our solar system plunges to Earth.
Vertigo Mach, your range is 10 miles now, sir. It's coming down through 200,000 feet. 10 miles, 200,000 feet, thank you.
Manager, we are able to identify a tumbling object, and Mission Manager MTC be advised, from our vantage point, we do not see a drogue chute. Negative drogue.
Copy.
NASA pulls back the recovery team, including the mid-air capture helicopters. Because the parachute deployment sequence is a fail-safe mechanical system triggered by re-entry, there is nothing NASA can do to activate the parachutes.
It looks like we have a no-shoot, sir. Vector 200,
Mission
put it on your
Manager.
nose, 8 miles, look for an impact.
Impact at 5855.
When the prized capsule slams into the Utah desert floor, a seismic, emotional shockwave strikes research labs around the world like a forged aluminum Icarus. NASA's flight to the sun has ended in tragedy. The SRC is in pieces, the sample capsule is breached, and the most carefully protected unmanned payload in NASA's entire history lies in a sunken crater of Dugway dirt. Dirt that's been exposed to 60 years of chemical and biological weapons testing. The recovery team is not allowed near the capsule because of toxic gases from the SRC's batteries and the unfired drogue chute explosives. As they wait for access, questions fill the air. What went wrong? And how bad is it? And what about the solar wind ions buried deep in the pure element collectors? After the gases dissipate and the explosive charges are disarmed, the NASA recovery team goes to work to recover even the tiniest of fragments of the collector arrays. The arrays and solar collectors, in 15,000 pieces, are carried with the buckets of debris and desert sand to an impromptu clean room. Scientists begin the painstaking process of separating the shattered arrays from sand and other wreckage, with the ultimate goal of determining if contamination has destroyed all scientific value in these priceless pieces of the ancient past. Meanwhile, NASA investigators want answers. How could a $100 million mission end in a devastating crash landing? The investigators focus their attention on the failure of the drogue chute. NASA has used parachute re-entry systems in one form or another since the very beginnings of the space program. It is regarded as a heritage system, and it always works. Well, almost always. When the capsule leaves the vacuum of space and hits the density of Earth's atmosphere, a switch called a gravity switch, or G-switch, is thrown forward, sending an electronic signal to 4 explosive charges that blast away a cover plate to deploy the drogue chute. Just like when driving a car and hitting the brakes, anything not secured will be thrown forward. The gravity switch works on the same principle. The force of the atmosphere meeting the momentum of the spacecraft and throwing the switch forward. The switch starts the automated landing sequence. There are very few ways it can fail because it is not computer or electronically activated. It is a rocker switch that simply rocks forward when the spacecraft hits the atmosphere. Genesis was equipped with 4 gravity switches, 2 primary and 2 backup switches, installed in case the 2 primary switches fail. Investigators recover both the primary and the backup gravity switches from the wreckage and find them perfectly intact and not activated. While scientists work tirelessly to salvage the solar wind ions, NASA is about to discover the shocking cause of the crash, the end of Genesis. With the Genesis capsule wrecked, and scientists trying desperately to determine what, if any, scientific material will survive, the crash investigators review the spacecraft's design plans and engineering paperwork. Everything appears in order. The paperwork indicates the gravity switches were installed properly, along with a drogue chute and parafoil. While frustration with the investigation builds, a small ray of hope begins to emerge from the science recovery team. Some of the collectors are still intact, and the pure element wafers appear to have done their job. Many of the long-sought ancient ions remain pristine and uncontaminated.
One of the collectors is a piece of gold foil. Think very, very thin aluminum foil, but it's gold instead, and so it's even more fragile. It was completely intact, not damaged at all.
While the scientists were feeling optimistic, the crash investigators were not. Then, an X-ray examination of the switches finally provides a breakthrough. The primary switches are backwards, and the backups, they are backward too. As the sample-return capsule entered the atmosphere at over 27,000 miles per hour, the dense atmosphere began resisting the spacecraft, which should have thrown the switch forward. But because it was installed backwards, the switch did not move. It could not be thrown into a forward position because it had been installed in the forward position. The drogue chute never deployed, causing the capsule to tumble out of control. So when the spacecraft hit the brakes, the switch was already forward and didn't move. Once again, human error had proven disastrous. A wide-ranging investigation revealed that another program's engineers had made some design changes to the avionics unit, which shifted the circuit boards and the gravity switches installed on them. A standard centrifuge test would have caught the problem, but the test was not performed because the Genesis avionics unit was delivered 4 months late for testing, and because the gravity switch was considered a heritage system that was approved without the test. But NASA concluded that the design changes should have required the additional testing. NASA learned from the mistake and implemented rigorous reviews and evaluations of all mission-critical systems for every mission, and issued notice that just because a system has a backup, it still must be checked as reliably as all other systems. The spectacular crash landing of the $100 million Genesis sample return capsule demonstrates the risks of human error to space exploration. But human ingenuity, resilience, and a lot of hard work ultimately salvaged the science. NASA declared that all the mission's primary objectives were achieved, and groundbreaking research continues to be conducted on recovered solar wind ions. Studies on oxygen and nitrogen isotopes, as well as neon and argon isotopes, have confirmed some solar theories and revealed surprising levels of oxygen in the sun. Research continues.
Just because we can't analyze something today, and most of what we're getting back we can analyze, wait 5 years.
As humans continue to reach for the stars, driven by the spirit of exploration and the joy of discovery, human error is always a possibility. But human determination will always find a way to fix the problem, to go further and discover more.